while the projector is trying to come on, let me go over just a couple of fairly straightforward announcements, hopefully. First and foremost, you may have seen an email on this. On this campus, they've been testing the fire alarm system, I think, just about a week now. Today should be the last day they're going to be doing it. That's what I read anyway. If they haven't already finished, the day would be the last day. So if you hear the alarm go off and you don't smell smoke or see fire or hear someone saying this is not a test or a drill, this is the real thing, then we just stay where we are. This is not going to be a drill. It's not anything except they're having to test out the system. Okay. Number 2. Next week, they're calling Cougar Connection Week. I don't know if you've heard or read about it. There's all sorts of posters. They're like this, only much bigger and easier to read on the doors and walls and scattered around the campus here. And here's what's going on. On Monday of next week, on our campus here, from 12 to 1, there is the Constitution Day program. That will be down in the faculty dining room. I don't know if you know where the cafeteria is. Just this side of the cafeteria is the faculty dining room. That's from 12 to 1 on Monday. On the Birmingham campus, it's Get On Board, Volunteer Fair. The locations are outside the library and sort of the open area there. That will be going on from 8 in the morning until 1 in the afternoon. I'll wait and announce to you on on Monday what's going on the rest of the week. If you are going over or going to be on the Birmingham campus between 8 and 1 in the morning, the Get On Board Volunteer Fair, there's a bunch of organizations here that you can choose to volunteer for, or student organizations that you can become a part of. I'll just read some of these that are hard to see. It's Big Brothers and Big Sisters, Ben Green Housing Authority, Bessemer Recreational Center, Faith Chapel, Girls Incorporated, Grace Home, and you get it, Girls Incorporated, no, Grace Home, Hands on Birmingham, Humane Society, Metro Changers, Oaks on Parkwood, Operation Hope, Powership Network, and Red Cross. And I think they may be going to have a blood drive sometime next week too. So do another thing with Red Cross. The student organizations that you can choose to sign up for and be a part of: Ambassadors, Athletics, Fine Arts, Honors College, Phi Beta Lambda, Scholars Bowl, SGA, Speech and Debate, Student Support Services, STEM. For some reason, they don't have the math club on here, okay? Okay, so please, if you're interested in doing the math club, it's also called the math team. There's a competition coming up probably next month. That's when it usually is, either October or November. You can still participate, and it's a lot of fun, and frankly, you learn a lot of math doing it. So I'll try to remember to read you about what's coming up Tuesday and Wednesday next time. Okay, one other issue. This has to do with my office hours. Today, normally I have office hours on Wednesdays from 2 to 4 here on this campus, because at 4 I have to leave to go to Birmingham East Campus to teach a physics class that starts at 4:30. However, today the dean has called a meeting and we have to be there. In fact, I'll be hard-pressed to be there by 2:30, but I'll get there as soon as I can, so I have to leave as soon as this class is over with and try to get over there by 2:30. And then it goes until 4, and that just gives me time to go to the East Campus and then teach my class then. So I will be leaving as soon as this class is over with and not coming back on this campus until tomorrow morning. So just to let you know that. Let me mark Jeremy here since he did show up. I'm sorry, Terrell here since he did show up. I don't know where I got Jeremy from. I saw his name down there at the bottom. Okay, now, There's a little paragraph or so. Oh. One more thing, okay? I think I told you last time, I asked and y'all said we're in agreement with it, that we go on and have a test on what we did in chapter 11. And I have it in here somewhere. It better be in here somewhere. I did it. Here we go. Oh, okay. Really simple test. But should get you started with this score. Okay. And that will be, let's see, Daniel Farmer's in this class, so I need to somehow get him his. I've got to work that out somehow, how to get him his. Okay. So, bottom of page 821, we're in now chapter 12, which is vector valued functions. This is where we ought to be in the course. 12.1 is also vector valued functions, same title as the chapter. At the bottom of the page there, it says in examples 1 and 2, you are given a vector valued function, we're asked to sketch the corresponding curves, which is not easy when they're three-dimensional, okay? The next two examples address the reverse problem, finding a vector valued function to represent a given graph. Of course, when the graph is described parametrically, representation by a vector value function is very straightforward. And here's the for instance here. To represent a line in space given by this, okay? And let's see if I can find something white to, let me see. Yeah, here's some white space. Well, I want to get my pen color changed. Okay. All right. It says to represent a line in space given by x equal 2 plus t, y is equal to 3t, and z is equal to 4 minus t. Okay? You simply use the vector valued function, and I mean that gives you the x, y, and z, so the vector valued function r as a function of t would then be x is 2 plus t I plus, and your y is 3t j, and your z is 4 minus t k. Okay? There's your vector. Now, when the set of parametric equations is not given, the problem of representing the graph and vector value function boils down to finding a set of parametric equations. If they give them to you, they're easy. If not, you have to find them. That's what they're getting at. Okay? Now, let's do example 3. Let's see if example 3 is going to show up here. No. So let's go back and do example 3. Okay. Okay. Represent this parabola. Y is equal to x squared plus 1. And I think you're going to find this is pretty simple, at least some of the time anyway. It said represent that parabola by a vector valued function. Okay? The vector valued function is going to look something like that top. It's not going to be that, but it's going to look something like that. R of t is equal to something times I equals something times j, so something times k. That's the why I'm usually hot all the time, and just suddenly my hands are freezing cold. I don't know why. And it's giving me the shivers and the sneezes. Okay. We need to know the parametric equations for x and y. And believe me, they are really simple. Okay? There's your vector, there's your parabola. Let's express that as a vector value function. And it's only going to be in 2 space, so that makes it a little easier anyway. Guess what? You can choose anything for x. What parameter you want to use? Everyone's favorite is t. Would you rather use something else? Can't be x or y. Probably not r. And not I, j, or k. But give me something. Is t okay? Okay. Watch this. Let, I can't write, x equal t. Then it's pretty obvious what y has to be. What would it have to be? T squared plus 1. And guess what? Here's your vector value function. R of t is equal to ti plus t squared plus 1 j. That's all there is to it, if it's written this simply. Now, you can have functions that are really complicated, and then you might have to do a lot more head scratching. But when they're fairly straightforward like this, choose basically your parameter to be the most independent variable that you have there, that is least involved, okay? And let that be your t, and then do the others in terms of that. So that's all you got, okay? So that's example 12. You could choose other parameters. You could choose x equals negative t, okay? And I don't know why you would want to do that, but then even that, your y would still be t squared plus 1. Still the same deal. The only difference is which direction it's heading. And this one that we chose, when x equal t, here's your parabola. You go up 1, and this is your parabola. This one that we have here, it goes in that direction, because x can be any real number. So it's going like that. If you had chosen x equal minus t, it's going in the opposite direction. That would be the only difference. Okay. Man, I may have to go down and clear my head, because the sneeze really got me going here. So let's do example 4, which also is not on the slide set. Man, it's hard to breathe. Sketch the space curve C represented by the intersection of the semi-ellipsoid, the intersection of the semi-ellipsoid, here's this semi-ellipsoid, x squared over 12 plus y squared over 24 plus z squared over 4 is equal to 1. Okay? Number 1, is that an ellipsoid, or are they leading us on here? What do you think? What is it that makes an ellipsoid?
Does that have a point zero or something like that?
Okay. Okay. The constant can't be 0 if that's what you said. It has to be a 1. That's true. All 3 of your variables, you have to have 3 variables to be a 3-dimensional figure like an ellipsoid, so you have to have all 3 variables. They're all squared. If one of them wasn't squared, it's going to be a paraboloid. But if all 3 are squared and all 3 are positive and the 1 is positive, that's going to be an ellipsoid. Okay? Now, what makes it a semi-ellipsoid is a little statement they do next. Z is greater than or equal to 0, meaning Z is positive only. So your ellipsoid would be basically a football type shape, kinda, you know, but you only got half of it. It's cut into, and you only got the top part of that dome there. Okay? Now, so sketch the space curve represented by the intersection of that ellipsoid, right there, and the parabolic cylinder, y is equal to x squared. Now that's not a paraboloid. To be a paraboloid, you'd have to have a z component as well. That's just a parabola, y is equal to x squared, that is a cylinder, goes up and down indefinitely. Okay. Now, let's pretend we have sketched it, okay? It's not an easy thing to do, and if you got your text, hopefully you can see it on there. They sketched it for you. Goodness gracious. He sketched it for you there. And then they also sketched the y is equal to x squared, and that cylinder goes up infinitely and down infinitely, but we only need it where it intersects that, so they have that picture there. Now, the intersect, and it says, okay, then find the vector value function to represent the graph. And the graph there is that line that is that intersection of the ellipsoid, the semi-ellipsoid, and the cylinder. Sorry about that. Man. All right. Now, so we know both of these things have to be true at the same time. Okay? And there is one kind of obvious things you could do. Instead of x squared here, you could put it in y. And that would be, or yeah. Well, let's see what happens if we did that. We'd have y over 12 plus y squared over 24 plus z squared over 4 equal 1. And that, again, is true for z's greater than or equal to 0. That's going to be parabola-like, but not exactly. Another thing you could have done is instead of y, you put in x squared. That would have been x squared over 12. And here's Justin. Okay. Well, we increased the size from last time when we only had 2 people here. We've got 3 today, so that's an improvement. All right. And put, instead of y, we put x squared. Well, you got a y squared here, so that would be plus x to the 4th over 24 plus z squared over 4. That's equal to 1. Frankly, I think that's a little more complicated. I think it would be a little bit better going with that. But, so either one will work, and again, your z has to be greater than or equal to 0. You get it down to 2 variables like we've gotten here, and then pick the more complicated one and let that be your parameter. So for instance, on this one, we could say let y
equal t. Okay? And then solve for z. That would be t over 12 plus t squared over 24 plus z squared over 4 equal 1. So you can subtract t over 12 from both sides. Okay, subtract t squared over 24 from both sides. Multiply both sides by 4. Okay, and then take a square root. Z is equal to, but we're only going to take the positive square root because z is always positive, and that would be the square root of 4 minus t over 3 minus t squared over 6. Okay, there is a parametric equation for z, and you could for that. There are basically an infinite number of these that you could do, and we're not going to do them. They show a different one. They took this one that I had down here and factored it, which would be fine too. I mean, it's perfectly legal what they're doing. All right. I'm not sure that one was worth very much effort, but that would be your parameterization. And I didn't say this, I should have. X would be the square root of t. X equals the square root of t. So there's the third. Now you have all three. Z's a complicated looking thing, Y is simple, X in between. Okay. But there's infinite number. The one they chose didn't have any roots in it. And you could probably get it by manipulating what we did. Okay. They said the natural choice was X equal T, and that would have been okay too. Yeah, because you do X equal T, Y is equal to T squared, and then solve for Z, and you've got the same type thing. So there's basically an infinite way of coming up with parametric equations. All right, that's, I know, messy, and I would go with the one they had in the book more than this one, but if you don't have your book, this will be fine too. Since there's an infinite number of them, that it's sort of hard to say, do this, and then say, oh, this is right, but yours is wrong. No, there's an infinite number that may be right. Not all of them will be right, but you could still have an infinite number that would be. All right. The next thing we're going to do is limits and continuity, which basically are things we did with one space, you know, when we're just dealing with equations, functions, and things like that. Those were important. They're also important here, but realize a vector value function is made up of equations. So really there's not going to be a lot different here, but there are going to be a few nuances. So as soon as we get through, we'll go on and do some of those. Okay. In fact, the way I did it was rather bizarre. The much easier way would be let X equal T, Y is equal to T squared, and then plug that stuff in and solve for Z. And it makes the Z messy, but all your mess is confined to Z. You don't have any mess in X and Y. They're pretty simple. All right. So let's move on to limits and continuity. Oh, you thought we were through with these. No, never finished with it. The definition of a limit of a vector-valued function. If R is a vector-valued function such that, and we're going to start with two space here, it's easier. R of t is equal to some f of t I plus g of t j. Then the limit of R of t as t approaches some value a, say, would just be the limit of f of t as t approaches a times I plus the limit as t approaches a of g of t times j. And by the way, that will give you a plane. You know, it's a vector value function in a plane. Okay, provided that f and g both have limits as t approaches a. If they don't, you can't take those limits. Okay. Now, if R is a vector value function such that R of t is f of ti plus g of tj plus h of tk, now you're in three space, and if that's what you're dealing with, then the limit as t approaches a of R of t is still be the same thing. The limit as t approaches a of f of t times I plus the limit as t approaches a of g of t times j, the limit as t approaches a of h of t k. That will be in space somewhere, and that, of course, you have to have f, g, and h having limits of t equal a as t approaches a. If they don't, you can't take those limits, but if you do, and most of the time, I think probably you do, then you would be in fine shape. So really, there's nothing really new here. You're taking limits ultimately of your functions, okay? It's a vector value function with those functions as your coordinates, but that's what you're taking the limits of. So here's kind of how that looks. I think this is on this page still. RT approaches some vector L as t approaches a, then the length of the vector RT minus L has to be approaching 0. That is, the magnitude of RT minus L, the thing is approaching 0 as t is approaching a. Now here's the sort of the graphical illustration of that. Here's your R of t, and it's going to be following this curve here, okay? Now, if here's a vector L up here, okay, R of t is somewhere here, as t is approaching, sorry, if R of t approaches the vector L as t approaches a, that means as t gets closer and closer to a, the R of t here is getting closer and closer to being the L vector. Now this is for increasing. If it's coming from that way, it would be approaching that way. Okay? Meaning that the subsequent R of t, this is the first one, the second one would be here, and that would be a shorter distance. Here would be a shorter distance, here would be a shorter distance, here, and ultimately the limit is going to be 0. Okay? As t approaches a, R of t approaches the limit L. For limit L to exist, it's not necessary that R of a be defined or that R of a be equal to L. It just means it needs to approach it as you get closer and closer. Now, this thing here, R of t minus L, this would be R of t minus L. That would have been down here somewhere. R of t minus L. These that I'm describing there are just located up there because R of t plus R of t minus L is just going to be R of t. So you see they do add up this way. So this is the difference between R of t and L. Okay. This line here, then it's that one, then it's that one, then it's that one, then it's that one, and it's approaching 0. Doesn't ever have to be equal to L, but it's approaching it as you get closer, as R approaches A. All right. Next definition extends the notion of continuity to vector value functions. We talked about limits, continuity. I had to talk about it because the limits are involved here. The vector value function R is continuous at a point given by t equal a when the limit of R of t exists as R of t as t approaches a. So in other words, you can't have a different value when t is equal to a than you would the limit as t approaches a. It has to be the same. So the limit as t approaches a of R of t has to equal R of a. And if that's true for every t, or for any value a, however you want to phrase that, then it's a continuous function, at least on the interval where that's true. The vector value function R is continuous on interval I when it's continuous at every point on the interval. That's what I'm saying there, for any value a. For any t, in other words. So, let's talk about this. Discuss the continuity of the vector valued function R of t is equal to ti plus aj plus a squared minus t squared, k, at t is equal to 0. Okay? Discuss the continuity there. Okay. You think there's any issue when t is equal to 0? Or as t is approaching 0? That would be 0i plus aj plus a squared k. Okay? Where a is any constant. It looks like to me that that's true for any, I want to say any real number t. The only thing that I have a little hesitancy on there I don't think there's a problem there either, is t is equal to a, that would be ai plus aj plus 0k. So that's okay. It would be a squared. Let's see what they say about it. I don't see a lot you can say about it, but let's see what they're driving at here. Okay. Yeah, it's nothing spectacular. As t is approaching 0, R of 0, or R of t would be approaching 0i plus aj plus a squared k. Okay? Because t is approaching 0. So there's no problem with anything there. It just would be that your R of t isn't going to 0, isn't doing anything like that. It's approaching some vector where your x is 0, so you're not leaving the yz plane, and it would be aj plus a squared k. It's almost like you just play with that set of toys, where those are the values. And they don't say anything about a. A could be any constant. Okay. Now, you can conclude that R is continuous at t is equal to 0. Okay? By similar reasoning, you can conclude that the vector value function R is continuous to all real number values of t, which we said earlier. For each value of a, the curve represented by the vector value function, that is a parabola, and you can think of each parabola as the intersection of the vertical plane with the hyperbolic parabola. Okay. That does not too much for me either. Let's just see what they do with it. As t approaches 0, the limit of t as t approaches 0 is 0. Well, you said all this. Limit of t approaches 0 of a is going to be a, and the limit of t approaches 0 of a squared minus t squared is going to be a squared. So you simply get this: 0i plus aj plus a squared k, which is just aj plus a squared k. Now, whoops. Okay. Because R of 0 is the same thing, so you can conclude, okay, remember what the rule is. If the limit here is equal to the value when you plug it in, then it's continuous. So that's all you had to do. Show that the limit was that. When you plug it in, you get the same thing. So therefore, it is continuous at t is equal to 0. By similar reasoning, you can conclude the vector value function R is continuous at all real number values of t. There is no limit to what you could put t as, so you're going to get that there. For each value of a, the curve represents the vector value function in its example. That's a parabola. Okay? For each value of a, you get a parabola. You can think of each parabola as the intersection of the vertical plane y is equal to a and the hyperbolic paraboloid, which is this one. Okay? Yeah, if you think of this way, y is equal to a, that's the vertical plane. Here's the y-axis, y is equal to a, there's a is equal to 4, here's a is equal to 2, here's a is equal to 0. You always get a parabola for every one of those values. So, y is equal to a, so this would be y, that would be y squared minus t squared, and think of this then. This is your x value. This is your y value. So this would be y squared minus x squared, basically. That is your z value. So you see that comes directly from there. Now, what difference does it make? I don't know. It's, yeah, manipulating, doing around, but I can't think of what else you can do to it. That's probably the last slide. It is. They don't do example 6. Let's see if we can do something with example 6. Okay. Determine the intervals on which the vector value function R of t, the vector function R of t is equal to ti plus the square root of t plus 1 j plus t squared plus 1 k. Okay, for which that vector value function is continuous. Okay, it says describe the intervals on which that is continuous. Does anyone see a problem anywhere? thinking a domain type problem. Right here, over there. No problem there, continuity wise. T can take on any value there. T can take on any value here. But what can it not be here? Okay. The thing in there can't be negative. T plus 1 cannot be negative. So you're right there. T plus 1 is has to be greater than or equal to 0. I don't know where less came from. Okay, T plus 1 has to be greater than or equal to 0. So subtract 1 from both sides, and you got T is greater than or equal to negative 1. Okay, that's your limitation there. Okay, so if it has to be that here, it has to be that here. It has to be that there. Okay, what do you have when you have T is greater than or equal to minus 1 there? You have, and this is your x value, your x value starts at minus 1 and goes past 0 and infinitely positive. Okay? Your j, it can only be positive values too. Okay? Because that's a principal square root, and you can't have any negatives there. And then your k, that z value is so t has to be greater than or equal to negative 1. So when t is equal to negative 1, you have 2k. That's going to be the minimum 2k, and then anything greater, well, when t is equal to 0, which is greater than negative 1, then you have k, okay, and when t is anything greater than 0, or even 0, then you have 1k. So you just take on values between the minimum you could ever get would be 1 for your z value, and the maximum could be anything. Just take t to be any large number, square it, and add 1 to it. You got an extraordinarily large number. So t is greater than negative 1 on the x-axis. T is a square root function, square root function t on the y, and then you have a parabolic looking distribution on j, on the z part, and the minimum value it could ever be would be 1. So that's, so basically R is continuous. All that I was saying, R is continuous on the interval from negative 1 to infinity. That's really all you had to say. Negative 1 to infinity, which is exactly what we said here. T is greater than negative 1. All right. And Muhammad is here. Okay. That finished finally, 12.1. Homework exercises here. Any of the odds 3 through 9. They're all at Calc Chat. 3 is at Calc View. Do 11 is at Calc Chat and Calc View. Do 13 or 15. They're both at Calc Chat. You can think about doing 17. It's at Calc Chat. Should be. Either 19 or 21. They're both at Calc Chat. Neither are at Calc View. Sorry. Any of the odds 23 to 29, they're all at Calc Chat. 25 is at Calc View. Any of the odds 31 to 37, they're all at Calc Chat. 31's at Calc View. Do 39, it's at Calc Chat. 41's at Calc Chat. 43 or 45, okay, both are at Calc Chat. Any of the odds 47 to 53, they're all at Calc Chat, 51's at Calc View. Okay, it's just sketching a curve, I guess. Any of the odds 55 to 61, they're all at Calc Chat, 55's at Calc View. So if you're having difficulty seeing or visualizing this, the Calc View is probably going to be a good resource. You'll have some resources at Calc Chat, but I think Calc View might go into more detail. You can try to do 63 if you'd like, and any of the odds 65 to 69, they're all at Calc Chat, 67's at Calc View, and then do any of the odds 71 to 75, they're all at Calc Chat, and 71's at Calc View. Oh, there's more. 81, you could take a look at that if you're interested. There's a proof of 83 and 85. You can look at those if you'd like. There's a think about it in 87 that you can either choose or not choose. Particle motion 89. And then they talk about the Witch of Agnesi, which is a very unfortunate mistranslation for several reasons. Agnesi was one of the earliest, and maybe almost only, early mathematicians who gained international reputation. I mean, this is early. That was introduced back in chapter 3, and to do some more stuff of it. Anyway, what was bad news is this famous female mathematician, I mean, way back, I was looking for the dates, they don't give the dates here, came up with a curve that was of great interest, you know, and looked like it might have several prominent features, positive features. And in translation from one language to another, the shape of that was being described, or something about it was being described, and the translators thought they were saying, well, something else than what they were saying of Agnesi. I can't remember exactly what it was, a curve or something. But anyway, it turned out the translation came out witch rather than, you know, whatever word they were looking for. And that's what it's been known of ever since. And, you know, if that had been a man, they wouldn't have even thought of witch of Agnesi because he was a man. But anyway, it was just sort of an early indication of sexism, probably. Though we can't say that for sure, we weren't there. So anyway, that finishes 12.1. So let's move on to 12.2. Oh, man. All right. This gets to be a little more interesting, doable. That other stuff, drawing, sketching, those are pretty painful. Here we're going to be doing things we can really do with all the tools already in hand. Okay. Chapter 12 is still vector-valued functions. 12.2 is differentiation and integration of vector-valued functions. I think you'll see that's pretty simple, straightforward processes. We'll first differentiate a vector-value function, then we'll integrate a vector-value function. So let's start with differentiation. The definition of a derivative of a vector-value function parallels the definition for real-valued functions. Okay? So what it was for a real-valued function, y prime would be the limit is, say, delta t approach 0 of y of
t plus delta t minus y of t over delta t. Okay? Well, for a vector value functions, r prime of t is the limit as, probably should have been saying delta x before, but t's are okay. Now it's almost definitely going to be a t or some other parameter. As your change of t is getting smaller and smaller and smaller, r of t plus delta t minus r of t. So the distance between those points is getting smaller, and the interval is getting smaller. For all t for which the limit exists. In other words, everything in here has to be able to be defined. If r prime does exist, then r is differentiable at t. If r double prime exists for all t on an open interval I, then r is differentiable on the interval I. Differentiability of vector value functions can be extended to closed intervals by considering one-sided limits. Not that we really want, okay? But that's your definition, just like before. And if you pursue that, the differentiation of vector value functions can be done on a component-by-component basis. And you'll find out this is the key for vector value functions. Just about everything we'll do just component by component. See why this is true? Let's do r of t, we're two space now, f of ti plus g of tj. Okay? Applying the definition to the derivative produces the following. So r prime of t is this limit delta t approaches 0, r of t plus delta t minus r of t over delta t.
That's the same formula that the previous, right?
Yeah, that's the same one as before. Okay? Now, so what do we do with that? It's the limit as f of, this r of t is f of tg of t. So r of t plus delta t would be f of t plus delta t plus g of t plus delta t. R of t would be f of t and g of t, okay? Now, so the first one would be f of t plus delta t I plus g of t plus delta t j. That would be this function. Minus f of t I minus f of t j. That's minus r of t. R of t is just simply that. So, group these things together by components. That's the limit of f of t plus delta t I minus f of t I. So f of t plus delta t minus f of t over delta t I plus g of t plus delta t minus g of t over delta t j. Well, this is just the derivative of f prime. That is f prime right there. Okay? Okay. They did one more step. They brought the limit inside the sum, which is a legal move. And then this is your f prime of t I plus g prime of t j. So when you're taking a derivative of a vector value function, just take the derivative of each component as you go. Okay? And if all of those are defined on the interval, that you're taking the derivative, you get, that's your answer. It's really straightforward. This important result is listed in theorem shown below. This is the same thing over again. If r of t is equal to f of ti plus g of tj, where f, what in the world is that in there? I don't know. Where f and g are differentiable functions of t, then r prime of t is f prime of ti plus g prime of tj. Just that. If it's a three-dimensional vector, it's f prime I plus g prime j plus h prime k. Just differentiate each function, the component of each of your, take the derivative of each component, okay, and leave the same relationship. Okay. Now, note that the derivative of a vector value function r is itself a vector valued function, okay? You go back here and look, the derivative of this function here is a vector, okay? With this as its I component, and this is its j component. So it also is a vector. Always will be a vector. The functions are just, you're taking derivatives of functions and they just have their values. Note the derivative, okay, we already said that. You can see from this figure that r prime of t is a vector tangent to the curve given by r of t and pointing in the direction of increasing t values. That's exactly, I would hope, what you would expect it to be. This is your vector r of t, which is following along the curve like that. That's your r of t. R prime of t would be the change of the x, change of y, change of z, each direction. And that's going to be a tangent line to this curve. And this curve, remember, is in 3 space. So whatever it's doing, the tangent line to that in the same direction that the t's are increasing, that's going to be your r prime of t. Okay? Now, what are these other 2 lines here? I guess it's r of t plus delta t. Here's r of t. Somewhere here is a delta t. Say it's out here somewhere. But here's r of t delta t. So it would be here. And the difference between this and this would be this line here. Okay? So what? Oh yeah. And then divide that by delta t. As delta t gets smaller and smaller and smaller, this, we used to call it a secant line. It's now a secant vector, you might say. It doesn't have to be touched. Yeah, oh, it is touching up there. And it just moves itself back here until it's a tangent vector, okay, to that curve. All right. Here's example 1. For here's a vector value function, r of t is equal to ti plus t squared plus 2j. Find r prime of t. Not going to be too hard. Whoa, let me get my pen back. Okay. R prime of t. You tell me what you think it would be. Here's your function r of t. You tell me what r prime of t would be. Pretty straightforward. Give me something. Oh, there's Jeremy. Okay. We're basically only missing Daniel, and he's trying to do it remotely, so basically perfect attendance. Way to go, team. We're taking the derivative of a vector valued function, r of t, which is ti plus t squared plus 2j. What is r prime? It'd be what? Did you say I? Yes. One I, or just I, plus 2 2tj. That's it. I plus 2tj. That is the derivative of that vector r. So r prime vector. Because, this is going to be hard to describe, r of t depends on just the x component depends on t alone. When you take the derivative of that, it's just going to be a constant, okay? In this case, 1, okay? And then the y value of the function is a parabolic type shape, and the derivative of that is going to be a linear type thing. So, but you don't have to draw it, you don't have to picture it, you just know it's that, because that's just straightforward derivative. And by the way, this example we're doing here is also at larsoncalculus.com. For an interactive version of that type of example, it may actually show a few more pictures and things of what you would want to see. Okay. But the second part says that then sketch the plane curve represented by r of t and the graphs of r of 1 and r prime of 1. Okay. Yuck.
Should have known they were going to say this. Sketch the plane curve represented by R of t. All right. Well, to sketch this is fairly straightforward. If you sort of do backwards of what we did before, this is telling us x of t is equal to t, and y of t is equal to t squared plus 2. So if you put that in, that's saying y is equal to, t was x, so that'd be x squared plus 2. So basically your plane curve here was go up 2 and draw your parabola. That's your sketch of R of t. Sketch the plane curve represented by R of t. There it is. Okay? Now, sketch the graphs of R of 1 and R prime of 1. And these are vectors. Well, R of 1, and you're in a plane. There's no 3 space here. It's in the plane. You're perfectly happy right here. So R of 1 would be I plus, you tell me, (3j), is that what you said? Perfect. 3j. Okay? So that would be right 1 up 3. Okay? So that would be right there. This would be the vector R of 1. Okay? And the vector R prime of 1. Well, let's do what that is. Your R prime of 1 would be what? I plus 2j. Okay? Well, I plus 2j, that would be right 1 and up 2. And I didn't draw this very well. Let's see, this would be 0, 2. This would be 1, 3. And the next one would be 4, no, well, yeah. But anyway, that vector would be something like this. Not as long as this one. This would be R prime of 1 would be this, what we just said, I plus 2j. Now, I chose to write it as the tangent line to that curve because that's what it represents. I could have written it down here, and that would have been something like this, but what does that tell you? That tells you nothing. We draw this up here, and now, yeah, you see it is tangent to the curve there. Okay? And I think that's all they wanted you to do. I sure hope so. Okay? So let's clear my scratch out of the way and see what they show. All right. Differentiate on a component by component basis. Derivative of t is 1. Derivative of t squared plus 2 is 2t. Done. So it's I plus 2tj. That's your R prime of t. Your R of 1, just plug in to original, and where t is 1, that would be I plus 3j. Okay? Oh wait, I'm sorry. They're now drawing the thing. The parametric equations could be x equal t and y is equal to t squared plus 2, which is basically what we just said. So the corresponding rectangular equation would be y is equal to x squared plus 2. Okay? Yeah. Okay? Now, when t is equal to 1, R of 1 is I plus 3j, R prime is I plus 2j. So if you draw this one as your R1, 1 plus 3j,
and then this one is 1 plus 2j. 1 this way, 2 up, and that gives you that point. This one is not on the curve. It may occasionally fall on the curve, but most of the time it will not be. This one, of course, since you're going from the origin, that needs to be on the curve. This is tangent to the curve, which the odds are it's not going to terminate at a point. The curve would have to come back on itself or something like that. So, okay. That's all there was to that. Not very much going on there. All right, now. Let's see if I can find where they are. They look like to me they're skipping example 2, so let's back up and do example 2. Okay. For the vector value function r of t is equal to cosine ti, and they write it with nothing. I find it helpful to put parentheses on it, okay? Plus sine of tj plus 2tk. Now, does anyone remember what that basically looks like? You don't have to, but I was just wondering if anyone did remember. Because we did something like this before. This is a helix. It's like a spring, slinky that you stretched out. It's on the xy plane, the trace of that is a circle. Okay, but it's going up on z, so that circle is rising and rising and rising. Going down too, if you want to go that direction. Okay, so there is your curve. That's the vector value function. Find each of the following. What is r prime of t? What's your r prime of t? Negative sine ti plus cosine t j plus 2k. Perfect. All right. What is r double prime of t? Negative. Negative cosine t, I. Cosine t I. Sorry, I'll get it out one way or another. Next. Minus sine t j. Done. Plus 0, exactly. Okay? Now, what would be r prime dot r double prime? R prime of t dotted with r double prime of t. Do you remember what a dot product is? Uh-oh. Remember what a dot product is? Okay. Okay. What you do is multiply the x of this times the x of that, plus the y of this times the y of that, plus the z of this times the z of that. You multiply each one, adding them together, what do you get out of it? A scalar number, not a vector. Dot product always produces a scalar. So that would be, you tell me. You tell me. Sine t cosine t minus sine t cosine t plus 0, right? And what does that add to? 0. Now, what does it mean for two vectors to be, the dot product to be 0? That has a very special meaning. Those two vectors must be perpendicular. So that means r prime and
r double prime for this vector perpendicular to each other. Okay? R prime and r double prime are perpendicular. Okay, how about r prime cross r double prime? Now, this one, I can guarantee you will not be zero. Why? The cross product of perpendicular vectors is a vector perpendicular to both of them. If neither of those are zero vectors, then it's not going to be a zero vector. Do you remember how we did the cross product? I know it was a long time ago. Yeah, you set up the determinant I, J, and K, and you're going to repeat I and J again. So let's go on and get them up there. And then what do you put under that? The components of that first vector, r prime. That would be a minus sine t, cosine t, 2 minus sine t, cosine t. Okay? And what do you put in the third row? The components are double prime. That's the second thing you're crossing. And that's minus cosine t minus sine t, 0. So that'll be minus cosine t minus sine t. Goodness, my writing's getting terrible. Oh, and it's about this time that my eyes dry out. I do not know why. The only thing I can figure is the heat coming off of this. I must be sitting right over it, and it dries out my eyes like crazy. All right, what do we do here? Your diagonals. There's the first one. What does that come out being? Multiplying those things together. 0. Okay, I can handle that. Doing the second one, what do you get? That should have gone through the 2. Minus 2 cosine t j. Okay, third down diagonal, what does that give you? Plus, notice, sine squared, isn't it? Sine squared t k, right? Everybody follow? Okay, then you do minus the up diagonals. And what does that first one give you?
Negative cosine squared.
Yes, except then it's minus of it, because that's a minus. So that's going to be a positive cosine squared tk, right? This one. This one. Plus 2 sine. I lost it. There it is. Yeah. I've got too many things. Sine ti. Okay. All right. And the last up one gives us absolutely nothing. Right? 0. Well, what's sine squared t plus cosine t squared t? Those are your j. That's 1. So what do we have? We have 2 sine ti minus 2 cosine tj plus k. All right, there we have it. Now, just an observation here. I don't know. Let's just leave it alone. There we have it. 2 sine ti. I was going to try to read something else into it. Minus 2 cosine tj plus k. Okay. All right. We did what they said. They didn't take us any further. The parameterization of the curve represented by the vector value function R of t equal fti plus g of tj plus h of tk is smooth on an open interval. This is a new, okay. This is a new slide. Here we go. The parameterization of the curve represented by this vector value function, R of t is equal f of ti plus g of tk plus h of tk, g of tj plus h of tk, is smooth on an open interval I when f prime, g prime, and h prime are continuous on I. Smooth when those first derivatives are continuous. Okay? And r prime of t is equal to 0 for any value t. And r prime of t is 0 for any value t on the interval. Okay, so that's going to be the requirement. First, the L prime, G prime, H prime have to be continuous on I. But secondly, for that to be smooth, the function has to be smooth. The r prime is not equal to t. Okay, I think I was saying equal to. I said, whoa, that's really bad. R prime of t is not equal to 0 for any value t on that interval I. Okay, that kind of makes sense. Okay, so first derivative can't be 0. Now that leads, I think, to example 3. All right. Find the intervals on which the epicycloid C, given by this parametric equation, R of t is equal to, or vector value equation, 5 cosine t minus cosine 5t I plus 5 sine t minus sine of 5t j, and this is a planar curve. It's not a spatial curve, okay? And this is 0, t is between 0 and 2 pi. We want the intervals on which those things are smooth. Okay. So what are we going to have to investigate for it to be smooth? Okay, let's go back and see. What is required for it to be smooth? When F prime and G prime, this problem doesn't have an H prime, are continuous. So let's go back and look at that. And then also where R prime is not 0 for any of the value t on the interval. Okay, so let's first do what's your F prime of t. This, by the way, is f of t. This is g of t. So what's your F prime of t? Negative 5 sine t. Can't throw away that. Okay. First part. Second. Plus 5 times sine of 5t. Okay. Now the question is that continuous? Yeah, sine functions are continuous everywhere. See, that was a requirement where these are continuous. So your F prime is continuous everywhere.
So that first 5 was a book.
Okay. If you wanted to, you could pull that out. In fact, I think I would rearrange it and write it as 5 times sine of 5t minus sine of t. If you want to do that, you can. You don't have to. It's fine. That's continuous everywhere. Sines are continuous everywhere, so sums of sines and differences of sines are continuous everywhere. Multiples of sines continuous everywhere. Let's see about g of t, g prime of t. What would that be? 5 cosine t minus 5 cosine 5t. Okay? So you could pull out the 5 there too if you wanted to. It doesn't really matter. Okay. All right. Now, those are continuous everywhere. So far it looks like it could be smooth everywhere. But it also has to be that r prime of t is not 0 for any value t on the interval. So let's see what r prime of t is. R prime of t is equal to what we just did. I'll write it the second way, 5 times sine of 5t minus sine of t. And that would be I. I'm getting lost here. Yeah, that's I. Plus 5 times cosine t minus cosine 5t j. Now, we have to find if there's any place where that is a 0 vector. Okay? For that to be a 0 vector, both of the components have to be 0 at the same time. So let's try it. Set this equal to 0, you can divide out the 5, and you get sine of 5t minus sine of t is equal to 0. Okay? Now, does that happen anywhere? Well, certainly when t is equal to 0, right? So, t is equal to 0, that would make that 0. Anything else? Let's think for a moment. Whoa, that hurts. All right. Boy, that's not an easy thing to fiddle with. Let's see if they have a shortcut in here. They just plop it on you. Okay. Well, let's go to another one, and I think we'll see this. When t is equal to, they say pi halves, and let's see what happens. When t is pi halves, what is sine of t? Sine of pi halves. One. Okay. What is sine of 5 halves t? 5 halves pi. Okay. Okay. Here's sine of 0, 1 half pi, 2 halves pi, 3 halves pi, 4 halves pi, 5 halves pi. You're right back at the same place. Sine is 1 there. So sure enough, that would be 0 at pi halves as well. Okay. How about at pi? Sine of pi is 0, and sine of 5 pi is 0. Okay, so at pi is also 0. How about at 3 halves pi? Okay. Sine of 3 halves pi would be 1. So that's going to be a minus 1. So this is going to be a plus 1. And sine of 15 halves pi, right? Okay, 15 halves pi. Let's see what that is. That's 1 short of 16 halves pi, which is 8 pi. 8 pi would be here, and sure enough, pi halves short of that would be down here. So yep, that would be 0 there too. And I think we can safely say at 2 pi as well, because everything at 2 pi is the same at 0, right? So I think we're safe there. How about the second one, where cosine, let's just do it this way. Cosine t equal cosine 5t. That's what we're looking for. Well, let's start with t equals 0 again, because they've got to be at the same time. So let's just use only these. Cosine of 0 is 0. Okay? No, it isn't. 1. Okay? Cosine of 5t. Okay? Wait. Cosine of 5 times 0 is 1. Yeah, 1, 1. So 0 is certainly going to be on both camps, right? T equals 0. Okay, about pi halves. Let's see if that would work. What is cosine of pi halves? It's 0. Okay? And cosine of 5 halves pi is 0 too. All your half pi's are 0. You know, every half pi is 0. Okay? So sure enough, that one is. So pi halves. I think we can safely say all the rest of them are going to fit too. Cosine of pi is -1, and cosine at 5 pi is also -1. Because the difference between those is 4 pi, right? Or 4t. So all these multiples of 4t, that's going to work. So all of these are going to work. Pi, 3 halves pi, and 2 pi. There would be more, but we're only limited to 0 to 2 pi. So at each of these, you don't have continuity, okay? And that's what we're looking for. At each of these places, you don't have continuity. But everywhere, I mean, you don't have smoothness, okay? They're all continuous, but you have smoothness. But you don't have smoothness at those points. And that's why, and most of you have your books, no, some of you don't. Let me do my best to draw these curves. And we're almost out of time, so let me get these drawn. Here's your y-axis, your x-axis, okay? Okay. It does something like this. Almost a clover leaf. Those are a bit more pointed at the nodes there, but they're smooth from 0 to 2 pi, but not at 2 pi. I mean 0 to pi halves, but not at 0, not at pi halves. They're not smooth there because they're pointed there. They're not smooth. They're smooth from pi halves to pi, but at neither endpoint. From pi to 3 halves pi, but at neither endpoint. And at pi 3 halves pi to 2 pi, but neither endpoint. So it's the open intervals of each of those. Okay? So that's where the smoothness occurs. Okay? Now, how are we doing? I think we can do one more slide maybe. Oh, wait. I forgot they showed this one. All right. Erase that link. Okay. Derivative, just like we did before, we got it. On the interval there, the only values for t for which r prime of t is 0i plus 0j are at your every half pi. 0, pi halves pi, 3 halves pi, and 2 pi. Okay? Therefore, it's smooth in between those, but not at those endpoints. So there's your picture. Almost as pretty as mine, isn't it? Don't answer that. Okay. It's not smooth at the points where it intersects the axes, but smooth otherwise. Okay? Now, such points where they are not smooth are either called cusps or nodes. These were definitely what I call cusps. Now, maybe they're called nodes too. I don't know. But here's the properties of your derivative. Okay? And these, hopefully, will not come as any surprise. If r and u are differentiable vector value functions of t,
W would be a differentiable real value function of t, and c is a scalar. Okay? Well, certainly the derivative of a scalar times a vector value function is c times the derivative of the vector value function. Okay? Derivative of one vector value function plus or minus the other vector value function is the derivative of this. So the derivative of a sum or a difference is the sum or the difference of those derivatives. Just like you would expect, I hope. Now, here's one. Derivative of a scalar function times a vector value function would be, and this is your product rule for vector value functions with a scalar. W times R prime of t plus W prime times R of t. Okay? Now, what if that were a dot product? Same type thing. Its derivative would be R dot U prime plus R prime dot U. Does it matter which one you prime first? No, because addition is commutative. It's going to give you a scalar answer. It doesn't matter which one you prime first. But this one, the derivative of a cross product, it does matter big time. Okay? R cross U prime plus R prime prime cross U. Well, I guess I said that wrong. The order doesn't matter. Let's see. No, I don't think it matters which one you prime first. You could have written this first and this second. That wouldn't have made any difference in the world. What does make a difference is you keep the order here the same. RU, RU, RU. Has to be that way. Which one you prime first doesn't matter, but it has to be kept here. This one, you could have said this is U prime dot R. It wouldn't make any difference. Oh, that's the same thing. And then number 6. Composite. The derivative of the composite of a vector value function with a scalar function is chain rule R prime at W times W prime. That's your chain rule. I don't think it makes any sense to do a W of R. We haven't even defined what that would be yet, so keep it like this. And then number 7, if R of t dot R of t is equal to C, then R of t dot R prime of t has to be equal to 0. Now, that is a bit bizarre because R dot R is always going to be a constant. Always going to be a constant. So that means R and its derivative of R are always going to be, the dot product going to be 0. And if that's the case, that means R and R prime are always perpendicular. So I don't know what that's meaning. R of t cross dot R of t is always going to be a constant. Any vector cross dotted another vector is going to be a. Well, let's see. I don't know. I don't see any way around that. But anyway, those are your 7 properties of the derivative. They do a little proof there of one of those, property 4, and a little exploration of in the gray box at the side, but then they move on to example 4, and that's all we've got time for. In fact, I think we ran over, didn't we? Did we a little bit?
Yes.
Huh? But no extra charge, okay? All right. All right. We'll begin next time at example 4. And I have a meeting I have to go to. I was going to end a little early, but I didn't. Okay, sorry. All right. Any questions? Yes? Oh. Some of you came in after I passed out the test, right? Is that what you were asking about? Okay. So let me find those again. Here we go. You. And I've got to somehow figure out a way to get to that. Hopefully he'll contact me, but if not, I'll have to contact him. Okay. Okay.